Sure.
Is when the modeling, you have to do anything, there's like finite difference.
Technically, yeah. So technically, you have to solve it with the computation method. Yeah, we're gonna use a finite difference like, yeah, we'll do next week though.
Can I submit pictures? I just-
Uh,
Or do you want me to save them in the?
I would, yeah, I would like a little higher quality.
Okay. And then do you need us to submit our?
Yes, yes, please.
Yo, parts for it. What's that called? Pokemon cards. My pat. My pat. I'm reading the writings. Let me open one. Hey, yo. Yeah, open one really quick. Go. Oh, he has another one. You got everyone. No, you got one. Oh, no, they gave it really smart. I was gonna give it to you. What am I guessing? I work with the anybody, bro. Not gonna keep
I don't think he does. I just need you to find me moving. Wait, what are you doing?
Is it the energy? Is it the energy? Yeah. Ah, you fuck. No, this doesn't feel like energy. I don't know. I think it's it's more. Other than that, it felt a little Chinese.
Oh, where's the fun?
My friend like park. You shouldn't have opened that. I got that terrible. Roger, I have to do it. 4 years.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Okay, so we're Thursday, week 8. So we have another set of lecture notes today. We're starting a new topic. So no more gross pictures of carne asada. You know, we're getting back to math here. So we're talking about the 1D equations today. Okay. Oh, my camera's really cool. Right. Okay, so some announcements. Remember, homework 2, the lump parameter modeling homework is due tomorrow. So make sure you guys get that in time. If you have questions on it, I don't have any more office hours this week, but you know, you can send me an email. I can help you out through that. And then besides that, I don't know when the next homework's going to be. I need to kind of think about it. But you know, after this week, I want you guys to start focusing on your midterm projects, right? So remember last weekend I sent you guys the your image data for the midterm project. So make sure you guys are starting to work on that, because I think you know, it's probably going to take you guys some time, because it's the image data is not as clean as the tutorial data set. So you want to make sure you give yourself enough time to work on. Okay. Speaking of the tutorial, I know I'm behind on grading on those. It's just kind of a hectic week, hectic past couple weeks with advising and everything like that. So I'm planning to grade it tomorrow. So you should know what you have on the tutorial tomorrow. Okay. All right. So that's all my announcements. Are there any questions I can answer before we get started for today? All right. Oh, actually, one more announcement. So this is not related to the class, but next Friday, the department is putting on a kind of like a social study hall kind of thing. So the idea is that, you know, on Friday afternoon from 4 to 6 p.m. In E201, the department's going to get like snacks and coffee for you guys. So you know, just to kind of give you a chance to kind of come there, you know, study, get some snacks and things like that. I'll be there, and so it'll be kind of like an additional office hours for this class. So if you want to come hang out, get some coffee, yeah, and it'll be next Friday. So I'll send a link out to everyone through the announcements today. If you could if you're interested in coming, please RSVP, just so that the department knows how many people to order food for, because I think probably some people are gonna come that didn't RSVP, but, we don't want to be short on coffee for people. We want to make sure everyone comes and is fed. That's usually good for these things, okay? All right, so let's go ahead and get started with the lecture today. So we are starting a new topic. We're starting 1D equations of blood flow. Zoom in so much like that. All right. So last time we kind of really did some lecture notes like this. We were talking about lump parameter model, right? And so the whole idea with lump parameter modeling was to give us a way, to take a very complicated phenomenon like blood flow and give us a way to solve it with math, and to basically model its behavior. Okay? And so it introduced this concept of modeling for us, where, whenever you have a very complicated physical phenomenon that you either need to analyze or design for or to work with from an engineering perspective, it helps a lot to have these models because, otherwise you're kind of stuck with either physical testing, physical observations, which have a lot of limitations. Okay. So having a model where you can solve things very quickly, you can write equations for, has a lot of advantages. Okay. But with that said, modeling also has a lot of disadvantages as well. And we saw quite a few of these with non-parameter model, right? So the main disadvantage of LPM was that it's a little bit too simple, right? And so it took a three-dimensional phenomenon, which is blood flow in your arteries, and simplified it to basically 0D circuits. Right? In particular, the main drawback of lump parameter modeling was its spatial resolution. Okay, and what that means is that when you're solving a lump parameter network, you're really only limited to being able to solve things at the nodes of the circuit or at the elements of the circuit. Okay? So for example, let me draw an image here to kind of illustrate kind of what that means. And so if we draw a typical bifurcation, right? So this is a very typical kind of geometry you would see in the cardiovascular system. So you have blood flow coming in, its path is going to split into two daughter vessels, and this kind of produces a lot of really interesting fluid mechanics, pressures, velocities, things like this. Right? If we were to represent this, if we were to model this using parameter modeling, it may look something like this. Like we may have an inductor coming in, followed by a capacitor, followed by a resistor. Okay, and then this is going to split. Maybe we have a resistor, capacitor, another resistor like this. Okay. Right. Might look something like that, or as soon as my iPad decides to catch up. There we go. Okay. So, we can do this. This is totally fine, right? But we're limited in this case. And so, the things we're solving for here, right? Remember, whenever we do our parameter modeling, we're essentially solving for the flows and pressures on all the inductors and capacitors, right? And so if we call this quantity 1, quantity 2, quantity 3, quantity 4, right? We're limited to those locations, right? And so quantity 1 and 2, we can kind of see that's for the parent branch, right? So quantity 1 and 2 would be the flow and the pressure in that parent branch. Quantity 3 would be the pressure in daughter branch 1. And quantity 4 would be the pressure in daughter branch 2. Okay. Right. But what if we were interested in kind of more local quantities, right? So what if we were interested in the difference in pressure, right? We'll use another color here. What if we were interested in the difference in pressure between this point, we'll call it point A, and point B, right? Okay. So basically right before you get to the bifurcation and a little bit upstream of that. Okay. Right now with this model, with our lump parameter modeling, this would be impossible to do because the pressures that we compute are, and we don't even know exactly where they are in the branch. They're just the pressure in that branch, right? Okay. So something like that, where where we want to kind of measure something kind of a very local quantity, with the limitations of lump parameter modeling, we just wouldn't be able to do that. Okay. And we have a lot of reasons to do something like this too, right? So remember we talked about last week, one quantity that doctors measure to measure the severity of a stenosis is fractional flow reserve. Right? Right. And so whenever you have plaque disease in your body, whenever you have atherosclerosis, the way the doctor kind of measures how severe it is or how impactful it is towards your health, they measure the pressure drop both before and after a stenosis. Okay. That's just one example, right? But of course, there's lots of other examples where you want to kind of measure kind of local quantities. Because a lot of cardiovascular disease is localized in places like this. Like you think of aneurysms, things like that, right? And our lump parameter modeling, it's good for a first impression, but it's not able to kind of do useful things like this. And so we need, with this, we know that we're going to need a more sophisticated, a more detailed modeling methodology. Okay. So that's basically the goal for this week. That's why we're getting into the 1D equation, because the 1D equations, they're a step up from lump parameter modeling, and they allow us to do these kinds of things. Okay. All right, so that's the motivation, right? And so we're kind of working our way up in complexity, right? Ultimately, the goal for this class is to get up to computational fluid dynamics. So that's fully 3D flow. That's what you guys are gonna be doing for your final project, but you know, we're kind of working our way up. So this is kind of step, you know, we did one parameter modeling, that's step one, 1D equations is step two. Then kind of before spring break, we're gonna be doing a lot of 2D stuff. So that would be kind of step three before we get to CN. Okay. All right, any questions on this so far? Yeah.
When we're doing low parameter modeling, it's like purely transient. So which part of the vessel, like, are we getting like our values from? Is it like the average of the entire vessel, or is it?
Exactly,
Okay.
yeah. So the assumption with lump parameter modeling, so I think maybe a better way to do it would be to, you know, we have this block right here. So this block kind of represents the average things in like in a block like this. Yeah.
The average from like just the entire volume of the.
Exactly, yeah. So there's ways that you can improve this. So you can kind of make more circuit blocks, so you can kind of copy and paste this to kind of get some spatial resolution like that. Then that kind of becomes a little cumbersome, and you know, you might as well just do 1D equations at that point. Right, any other questions on this? Okay. So how do we get the 1D equations? So I'm going to call, you know, we call these the 1D equations of blood flow, but we're actually going to derive them straight from Navier-Stokes, right? So the 1D equations of blood flow are derived they're derived primarily by integrating the Navier-Stokes equations across the cross-sectional area of a blood vessel. So there's still a little bit of averaging here, you know, because we're not doing the full Navier-Stokes, but instead of averaging over an entire volume, we're averaging over a slice instead. Right? And so we still kind of retain basically spatial resolution in the flow direction, right? Right. So actually, that's let me kind of illustrate that just because I think that's kind of a good point, right? So if we have a blood vessel, right? If we were to do this with lump parameter modeling, you know, and we had a chunk of a circuit, you know, the chunk of circuit would represent this entire volume. Okay. So if we have a circuit, right? That circuit element right there, the inductor, the capacitor, and the resistor represents that entire volume, right? Whereas for 1D modeling, right, we're instead going to look at a particular slice. And so a slice, you know, let's say that we take a slice like this. So we're going to average everything in that slice right there. Okay. And so we're still going to retain freedom, but we're still going to retain a variable in the z direction. So we're going to use the z variable here to represent the flow direction. Right? But everything kind of perpendicular to that z, everything in that cross section, we're going to average, we're going to integrate. Okay. All right. So the outputs or kind of what we're going to be solving for in the 1D equations. Okay. we're primarily going to be looking for two variables. And so the first thing we're going to be solving for is the flow rate. Okay. But unlike the lump parameter modeling, this is no longer just going to be a function of time. Okay. Now this flow rate is going to be a function of both space, a one dimension of space, which is z, and time. So that's the first output. And I think that's probably the obvious one that kind of comes out of this, right? And so if you remember from our fluids review, when we took our velocity profile and we integrated it across the cross section, we got flow rate, right? And so if we take our Navier-Stokes equations, we integrate across the cross section, it makes sense that we get flow, right? So that this one, you know, we could have seen coming. The other variable that actually is interesting is the cross-sectional area of that slice, which is also going to be a function of z and t. So this tells us that locally our cross-sectional area may actually vary, right? And so if we were to draw a vessel like this, right? The fact that the cross-sectional area is a variable basically means this, right? And so if we were to take slices, on one slice, you know, we may have a certain cross-sectional area given by the area that's shaded portion there. Okay. If we go down the vessel a bit more, you know, maybe the vessel has locally expanded a little bit. Okay. But then you go down a little bit more, the vessel may contract. So it may come back down to a small area like this, right? And so basically the 1D equations are letting us, of course, it's going to allow for us to have kind of local variations in the cross-sectional area. And this is important because one thing that's really important for blood flow that we've kind of talked a lot about is that the vessel walls are flexible. Okay. That's the reason we have capacitors in our lump parameter model, right? And so, you know, we're kind of losing the capacitor, so we don't have the capacitor to model this anymore. And so we need another way to kind of incorporate that into our equations. And so the way that we do that in the 1D equations is to solve for the area as one of our solutions. Okay. So those are the two main outputs we're looking for in the 1D equations. We're going to look for equations for the flow rate and then equations for the cross-sectional area as well, right? The pressure is going to be there too. Technically, we are solving for the pressure, but we're going to use another equation for that. Pressure will come a lot later in the process. But for now, we're just going to focus on flow rate and cross-sectional area. Okay. Any questions on this so far? Yes.
It's assuming that cross section stays constant though. Well, because doesn't that happen doesn't it expand as it flows?
It does, but then you know you might have pressure pulses that go down as well, so that might cause the area to expand and contract locally like that. So it's not going to be as extreme as this where you have like a wavy thing going on, but you know you might have certain, like when the heart pumps, like the entire vessel may expand and then it's going to contract like this too. So having this as a variable allows us to do that, basically. Okay, all right, so let's start with the derivation now. All right, so we're gonna spend, and I'll tell you, we're gonna spend the rest of today doing this, and then probably some of Tuesday as well. I hope you guys like integrals. Hope you guys like lots of calculus, because we're going to be doing a lot of it. Okay, so our starting point for our derivations is going to be our Navier-Stokes equation. So that's conservation of mass and momentum for a flowing fluid in cylindrical coordinates. So I'm going to start with the full equations, and so we're going to write out the entire cylindrical Navier-Stokes in all its glory. But of course, we're going to apply assumptions for this and simplifications, and so we're going to be basically working on these equations throughout this entire next couple of lectures. Okay, let's start with the mass equation first. Okay, so the conservation of mass equation we have in cylindrical coordinates, we have 1 over r, partial r u sub r plus 1 over r partial theta of u sub theta plus partial uz partial z, and all this is equal to 0. Okay. So that's our continuity equation in cylindrical coordinates. All right, next we have our momentum equation. And remember, in Navier-Stokes, we have momentum equations in all 3 directions. We have a momentum equation in the r direction, in the theta direction, and the z direction. For the 1D equations, we're just going to focus on the z direction. So we're just going to have one of the momentum equations, one of 3. Okay. All right, so we start with partial uz partial t plus ur partial uz partial r plus u theta over r partial uz partial theta plus uz partial z. This is equal to, or excuse me, yeah, that's fine, minus 1 over rho. Rho here is density, partial p partial z plus, we go to the next line here, mu over r partial r of r partial uz partial r plus mu partial squared uz partial theta squared plus mu over r squared partial squared I'm sorry, so this second to last one is partial z squared on the bottom, and this one here is the theta. Okay. So it's a lot of terms, right? But that's Navier-Stokes. Navier-Stokes is always a ton of terms in Navier-Stokes. All right. So what we're going to be doing today, for the rest of class, basically, is we're going to be taking these equations and integrating them across a cross section, right? And so, a big part of today is just kind of using calculus, using what we know about integrals and different and derivatives, and manipulate the terms to kind of get them in a convenient form. Okay. But before we do that, we can simplify this a little bit already, before we start to get to work. So let's state one of our assumptions. Okay. So let's assume that we're going to have axisymmetric flow. So that means the flow is not going to depend on theta. So basically all derivatives that have theta, we're going to just eliminate them from the equation. Okay. And so in the continuity equation, I see one term that has theta. And so we have the 1 over r partial theta, partial u theta, partial theta. So we're going to set this as equal to 0. Okay. Right. And the reason is it's because there's a derivative with respect to theta. Okay. We have another one here in the momentum equation on the left-hand side. So we have the u theta over r partial uc partial theta. This one we're also going to cancel out for the same reason. Partial theta is equal to 0. And then we have this last term right here. We're also going to set this equal to 0. Again, because we have the partial theta in there, right? So basically any derivatives that involve theta, we're going to set equal to 0. Okay. So I want to do this one kind of right off the bat, just because it helps us simplify quite a bit. And it's a pretty typical assumption that you make working in cylindrical coordinates as well, because working with the theta derivative is it gets a little bit messy. So we'll go ahead and eliminate that one right off the bat. Okay. Okay. With that said, there are more assumptions that we're making. Okay. So that'll be kind of assumption 1. Assumption 2 is we're going to assume that the pressure P right? The pressure P is going to be uniform across a cross section. Right? That's going to have implications later. So basically, when we integrate the pressure over the cross section, it's just going to be it's just going to pull out of the integral. Okay. Another thing we're going to consider here is that we're only going to consider the axial component of velocity. So we're primarily going to be considered with u sub z. Okay. Most of our velocities here are u sub z, but there are a couple u sub r's as well. Okay. Okay. The radial velocity, basically u sub r, the radial velocity will only be evaluated at the vessel walls, okay? And so the vessel walls being R is equal to big R, okay? So little r is our radius coordinate, and then big R is the actual radius of the vessel itself, okay? In fact, because we're assuming that our blood vessels are flexible and that they can freely expand and contract in response to the flow, right? If we evaluate the radial velocity at the vessel wall, right? This is exactly going to equal to the wall velocity itself. There's going to be partial R, partial T. Okay. So basically that means that when the wall is deforming, right? And so we have kind of a standard vessel like this, right? And so let's say that we're looking at this vessel as it's expanding, right? So it's basically, becoming something like this, right? The walls are kind of pushing out, right? The velocity at which the walls are pushing out, that is partial R, partial T. Okay. So the radial fluid velocity is going to be directly equal to that wall velocity. All right, so whenever we see the radial velocity in our equations, we're going to evaluate it at the wall, and we're going to set it equal to the wall velocity, right? That's going to come into play once we start factoring in the cross-sectional area. Okay. All right, number 5, assumption number 5. Assumption 5 is a pretty standard assumption for fluid mechanics, and that's going to be the no slip condition, right? And so at the vessel wall, our radial velocity is going to equal to 0. Okay. So U sub z, when little r is equal to big R, is going to equal 0. Okay. Notice the differences between assumption 4 and assumption 5. So assumption 4 is an assumption on U sub r, which is the radial velocity pushing outwards, and assumption 5 is an assumption on the axial velocity U sub z. Okay. Right, and finally, assumption 6. Assumption 6, not really an assumption, but it's kind of more of a reminder. And so assumption 6 here is just a reminder of how we compute the flow rate. Okay. All right, so the flow rate through a cylindrical vessel, is given by Q is equal to 2 pi integral from 0 to big R of U sub z, which is a function of R, multiplied by R dr. Okay. And so when we see this expression in our derivation, we're just going to plug in Q for this. All right, so it's a lot of assumptions, you know, but they'll all kind of come into play. And as we're going through the derivation, you know, I'll kind of remind you of all these assumptions, kind of when they become relevant. But it's, you know, just like any derivation, you know, it's important to state all these assumptions first, so that, you know, we can kind of get the ball rolling once we start. Okay. All right, any questions on these assumptions here? Yeah.
Is it B or little r inside the parentheses?
That's a little r. Thank you. All right, so let's go ahead and get started on the derivation then. Okay, so let's start with the conservation of mass equation. This is almost like the tutorial level. So this is the you know, kind of the, you know, if you play video games, you know, this is the level that you play just to get used to the controls, see how things are going before you end up doing the real level, which is the momentum equation, right? Okay, so let's write out our continuity equation again, right? So our continuity equation, we come back up here, you know, it's going to be this equation up here, of course, but without the theta term. Okay. All right. So we have 1 over r, partial r of r, u sub r, okay, plus partial uz, partial z, and all that's equal to 0. Okay. That's our remaining continuity equation after we cancel out the theta term. Okay. All right. So what we're going to do to this equation is we're going to integrate each of the terms across the cross section. Okay. What that means is basically we're going to multiply every term by 2 pi. Okay. We're going to integrate each term from 0 to big R. Okay. Inside the parentheses there is going to be basically each term of that equation. And then we're going to multiply by R dr, right? So we're basically, you know, applying the same thing for the flow rate, right? So if you look at our equation for the flow rate, you know, that uz of r there, that's kind of our ellipsis, that's our parentheses, right? So we're going to multiply by 2 pi, integrate from 0 to big R, r dr. Okay, so we're going to do that for every single term in this mass conservation, which is 2. Okay. Okay. So let's do that. So we have 1 over r. Well, we have the 1 over r term, so we're going to multiply by 2 pi. Okay. Integral from 0 to big R of 1 over r partial r of r u r. Okay. Multiplied by r dr. Okay. So I use colors here so that, you know, and the red right there, that's what we're applying. That's the integration across the cross section. And then in the black there, that's just the term that's directly from the continuity equation. Okay. So hopefully those colors are helpful. Then we're going to do the same thing for the uz term. For the uz term, we're going to do plus 2 pi integral from 0 to big R of partial uz partial z of r dr, and all this is equal to 0. Okay. All right. So we have our two terms here, right? And so the next step here is to evaluate these integrals or simplify this as best as we can. All right, any questions on how we got to this point here though? Right. So these are long derivations, and so we're basically doing a 45-minute derivation today. So it's important to kind of stay with these long derivations. There's a lot of steps and there's a lot of symbols and variables flying around. So kind of you want to make sure that you're kind of understanding every step of the process, okay? Because it's very easy to kind of get lost in the details. So I'm going to do my best to kind of try to explain the purpose of each step. I think with these long derivations, it's always helpful to know kind of why we're doing each step the way we're doing. But again, it's a process, and so you want to make sure you take it slow and ask questions if you're not sure kind of why we did a certain step. Okay, so we're gonna do these, because these are two separate integrals here. We're gonna work on them one by one. Okay, let's work on the first integral first. Okay, so this first integral, we have 2 pi integral from 0 to big R of 1 over R partial R of R UR times R dr. Okay. First thing we notice is that we have an R that's kind of floating around on the outside of that derivative, right? So this 1 over R and this R right here, okay, these are going to cancel out each other. So it's basically R over R. Okay. And then what we're left with is 2 pi integral from 0 to big R of partial R of R UR dr. Okay. All right. And so what we have there is a derivative with respect to R and an R differential from the integral. Okay. So I'm going to perform what some people call mathematical sacrilege. I call it a pro gamer move. So it's all kind of up to your interpretation. And so I can see here that we have a partial R on the bottom and a dr up top, right? So these are the same. So we're just going to cancel these out. Okay. And so all we're left with here is an integral. And I'm going to change that partial up top to a d, right? So we have integral from 0 to R of dr. Okay. So if you've never seen this in a class before, whenever you have the d in a symbol, this right here is known as a perfect differential. Okay. And the perfect differential is actually the opposite operation as an integral. So this perfect differential, this d, is going to cancel out with this integral up here. Okay. It's not going to perfectly, well, it's going to cancel, but we still have to evaluate the bounds of that integration. Okay. All right, so then what we're left with after that is we have 2 pi times the quantity inside that perfect differential, which is an R UR. Okay. Okay. And we're going to evaluate everything in the brackets here. We're going to evaluate it at R is equal to 0 and then R is equal to big R. So it's almost as if we did evaluate the integral. It's just we did it in kind of a cheap way. We kind of skipped some steps a little bit, but I think this kind of makes the most that always has made the most sense to me. Okay. All right, so let's go ahead and do that. So kind of imagine that we just evaluated this integral here. So we have 2 pi Everywhere we see little r, we're gonna plug in big R for that. So we have big R multiplied by UR evaluated at big R. Okay. So I've kind of left it off there, but that radial velocity UR is still a function of little r, right? Minus 0 multiplied by UR at R is equal to 0. Okay. So to go from this step to this step, I just evaluated integration bounds. Okay. All right, so from here, we know the second term is just going to be 0. How do we know? Because we have 0 multiplied by something, so 0 always wins, and so this is going to cancel out. Okay. Doesn't matter what the radial velocity is at r is equal to 0, it's not going to defeat 0, so 0 multiplied by that is 0. Okay. We actually have an expression for this, right? So this right here is the radial velocity evaluated at the vessel wall we actually have an expression for this. And so if you look back, you scroll all the way back up here to our assumptions. Okay. We look at assumption number 4, right? Whenever we have our radial velocity evaluated at the wall, we know that that's going to be equal to the wall velocity, right? So let's go ahead and substitute that in. Okay. And so if we do that, we get 2 pi r times dr, or partial r partial t. Okay. I'm going to do another kind of a weird move here. Okay, so we have r times dr dt basically, right? So if we do kind of a reverse chain rule, I don't know what else to call it. It really is just chain rule in reverse, right? We know that if we take d dt of r squared, right? Right, and we know r itself is a function of t, then by chain rule, we know this is partial r times dr dt, right? And so by reverse chain rule, and so if we go back this way, then we know that that quantity r partial t is equal to 2 pi partial t of r squared. Okay. I'll go back over this whole thing, but you know, there's a lot of steps to this thing, but it simplifies beautifully. You'll see in a bit. Okay. All right. So we're almost done here. So the next thing we're going to do, because that 2 pi there, that 2 pi is just a constant. So I'm just going to bring that inside the integration there, or the derivative, I should say. Oh, I'm sorry. This 2 also goes away because of the reverse chain. Yeah, so if you do d dt of r squared, you get 2r times dr dt. Right? So we just left with pi. So we bring that pi to the inside, you get partial t of pi r squared, right? We know what pi r squared is. Pi r squared is the formula for the area of a circle. Okay. And so we get the final form for this expression here, which is partial a partial t. all that work, all that integration, and we end up with kind of something simple like this. And so it's beautiful, but at the same time, you know, it took a lot of steps to took a lot of steps to get here. Okay. Okay. Any questions on how we got that? How we got that expression there? Exactly. Yeah. So basically, what I did was that, you know, I said that this expression here is equal to pi times 2r partial t. And since I know that r is a function of t, then I did kind of a reverse chain rule. So I substituted this for this. So this gets plugged into it right here. Yeah. Mhm. Okay. All right. So where we started was with this guy, right? So this entire kind of monstrosity of an integral just became partial a partial t. Okay, so very nice and convenient for that one. Okay, let's work on the second integral now. So let's work on this integral right here. Thankfully, this one's a lot shorter, so you know, no, don't worry about that. So this integral here is 2 pi integral from 0 to big R partial uz partial z times r dr. Okay. So with this integral here, you can see that we almost have the flow rate, right? And so if you look at our formula for the flow rate Q, right? Our formula for the flow rate Q is 2 pi times integral from 0 to big R of uz r dr, right? We almost have that. The only thing that's kind of in the way is that our z derivative, right? Okay, so we just have that partial z that's kind of in the way. So if we can deal with that somehow, then we can just substitute our flow rate into this equation right here. Okay. All right, but we're in luck, right? If you look at our integration that we're doing here, we're doing our integration in the r direction, right? The radial direction. The radial direction and the z direction are perpendicular to each other. And so essentially what that buys for us is that r and z are kind of independent. So that means we can kind of move things around. So we can basically take that z derivative and kind of pull it out from the entire expression. Right? So this expression here, and the fact that we have the 2 pi, we only have 2 pi out there as well. So there's really no worries that we can do this. Is that an equivalent expression is to take that z derivative and kind of pull it out to the front. So we have partial z of quantity 2 pi integral from 0 to big R uz r dr. All right, so this is good because now what we have in the square brackets here is that this is our formula for the flow rate. So let's go ahead and plug this in. And so if we plug that in, and then of course we apply the z derivative, then this term becomes partial q partial z. Okay. And that right there is our answer. Okay. All right. And so if we combine these two terms, right? So we combine our term from the first integral, we combine our term for the second integral, then we have our new 1D continuity equation. Okay. We have partial A, partial T, plus partial Q, partial Z is equal to 0. All right, so pretty simple result. It's still a partial differential equation, so we can't solve this by itself, but at least this kind of gives us something. Okay. So what this equation is telling us is that the time rate of change of area at a fixed position in space Okay. If we add this together to the spatial change in flow rate as you go along the vessel itself, okay, these two quantities added together have to equal to 0. Okay. And this right here is an expression of conservation of nets. All right. This makes a lot of sense. When you kind of write it out in words, it makes sense considering what we know about the cardiovascular system. Okay. So let me give you an example. This is kind of just a thought example of how this equation kind of lines up with, let's look at an expanding vessel. Okay. All right. So for an expanding vessel, we have our vessel like this, right? Let's say that there's kind of one area where the expansion has happened. So it's kind of happening like this. Okay. So as the vessel expands, we know that the cross-sectional area is going to increase. Okay. So that means partial A, partial T is going to be greater than 0, right? Because that's what the rate of change represents, right? So rate of change, if it's positive, then it's going up. Okay. At the same time, right? To cause this expansion, we know that flow has to be coming in, right? Flow comes in here, and some of the flow is going to go towards expanding the vessel, right? And so if you look at the amount of flow rate that's actually going down the vessel and passing through, that's actually decreasing because some of the flow is actually going towards the expansion. Because if the blood flow is going towards pushing the wall outward, it's not flowing through the vessel itself. And so what we can say is that partial Q, partial Z is less than 0 in that case, right? So that kind of makes intuitive sense to us. And so if we kind of take these expressions, right, and we plug them back into our continuity equation, if partial A partial T is greater than 0, in order for that entire expression to be 0, then partial Q partial Z must be less than 0 to compensate, right? So there's kind of an inverse relationship between these two quantities, right? And that's what the continuity equation represents. All right. Any questions on that? Okay. So we did a lot of math to get here, but whenever you're going through these kind of long derivations, it's always good to kind of pause, take a step back, look at the terms that you have, and make sure that it's making physical sense to you. Okay. So that's kind of what we did here. All right. That was the tutorial. So now we're ready for the real challenge here, which is the momentum equation. All right. So let's write out every term in the momentum equation. So there's going to be 6 of them, and we're going to write out. We're going to integrate each and every one of them. Okay. All right. So our momentum equation again. Let me go ahead and write it from scratch. So we have partial UZ, partial T, plus UZ, partial UZ, partial Z. Okay. Plus UR, partial UZ, partial R. This is equal to minus 1 over rho, partial P, partial Z. Now we have our 2 viscous terms, plus nu over R, partial R, R, partial UZ, partial R, plus nu, partial squared UZ, partial Z squared. Okay. Six terms. So let me label them here. So term 1, term 2, term 3, term 4, term 5, and this will be term 6. Okay. All right, so just like we did with the continuity equation, we're going to take each of these terms and we're going to integrate them across the cross section of the vessel. All right, I'm not going to write out the whole equation with each term integrated because we're going to tackle each integration one by one. Okay, so we'll start with a couple easy ones, and then we'll probably end it on that. Okay. Okay, let's start with term 1 here. This is probably the easiest one. Okay. So term 1, we have 2 pi integral from 0 to big R of partial UZ partial T R dr. Okay. All right, so for this one, we're going to do the exact same thing we did with the second integral of the continuity equation. And so you can see here that we almost have our equation for flow. The only thing that's kind of in the way is the time derivative. But The relationship between the time derivative and r is the same as the relationship between z and r. And so we can take this time derivative and pull it out of the entire integration. Okay? And so this is equal to partial t of quantity 2 pi integral from 0 to r uz r dr. Okay. So I pulled out the time derivative. Okay. And so by doing that, everything inside the square bracket we know is equal to the flow rate. Okay. And so we plug that in, then this first integral just becomes partial q partial t. Okay. Nice and easy. Starting off easy. All right, let's look at term number 2 here. Term number 2, we have 2 pi integral from 0 to big R of uz partial z r dr. Okay. For this one too, we're going to employ a tactic that we've already seen today. Okay. So this term right here, this uz partial z, right? Let's employ our reverse chain rule. Okay. Whenever you have a quantity multiplied by the derivative of the same quantity, that's a pretty good candidate for a reverse chain rule. Okay. We're going to take advantage of the fact that partial z of uz squared is equal to 2 uz partial z. Okay. And so we're going to plug in for this, but in the reverse, right? And so we have a 2 uz partial z. And so if we plug in for that, we get pi integral of 0 to big R of partial z of uz squared r dr. Okay. Okay. We're not done with this term yet, but you know, we've kind of hit a wall, and so we'll kind of deal with this later. So once we kind of see a few of the other terms shake out, you know, we'll know what to do with this one. So we'll leave it like this for now. Okay. All right. Okay, so the next term that we're going to integrate here is term 3. That one's going to be a little bit of a journey just because we have the r derivative, and so we can't just pull that one out. So I think we'll save that one for next week because I think that one's a little bit too intense to start now. And I think we've seen enough integrals and derivatives for today anyway. So, all right, any final questions before we wrap it up for today? Okay, all right. So we'll pick this up on Tuesday. We'll continue with the derivation. We'll integrate the rest of those terms and we'll get our 1D equations from there. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend, and I will see you guys next week.
I wouldn't go down.
saying like on the derivative of. How many is used for this is if they have. I'm the derivative of inside. It's usually some derivative of cosine. It's like that.
Oh.
Yeah.
You find your time function,
Yeah.
or like.
It's just saying like the function.
It's itself.
The derivative of what's inside.
Yeah, it's equal to itself times the derivative of it.
That's what it said. It also makes more sense if you. But then.
I was thinking of it as like this. X plus one. Yeah. Your parentheses square, I'm like, wait, I'm not, they not make sense.
What about people? And it's longer.
Yeah, no, I'm thinking about it.
I think you're gross.
It's chain rules, so yeah, you take the power, multiply it as a scale.
It's gonna take weird.
Yeah, I got you.
You're not getting a degree.
You add Celsius to Kelvin and you lose a whole letter grade. So.
Yeah. So did you ask them?
I'll go ask him and be like,
I mean, he's pretty.
I shouldn't be missing point, like, I get minus